Imagine a one-way street for electrical current. That's essentially what a diode is. It's a simple semiconductor device that allows current to flow in only one direction. Diodes have a simple structure with two terminals, an anode and a cathode. When a positive voltage is applied to the anode and a negative voltage to the cathode, the diode is forward biased and allows current to flow. However, if the voltage is reversed, the diode becomes reverse biased, effectively blocking the current flow. This unidirectional behavior of diodes makes them crucial building blocks in numerous electronic applications. Think of a diode as a valve in a water pipe. It only lets water flow in one direction, preventing any backflow. Similarly, a diode ensures that electricity flows through a circuit in the desired direction, preventing any unwanted reverse currents. Now, let's talk about freewheeling diodes. These are special types of diodes that are primarily used to protect other electronic components in a circuit. They are also known as flyback diodes because they provide a safe path for the flyback voltage generated by inductive loads when they are switched off. Freewheeling diodes are connected in parallel with inductive loads like motors, solenoids, and relays. When these loads are switched off, the collapsing magnetic field induces a high voltage spike in the opposite direction. This voltage spike can be detrimental to other components in the circuit, potentially causing damage. This is where freewheeling diodes come to the rescue. Here's how freewheeling diodes work. When an inductive load is energized, current flows through it, building up a magnetic field around it. When the load is switched off, the magnetic field collapses, inducing a voltage spike in the opposite direction. This spike has the potential to damage the switching device or other sensitive components in the circuit. The freewheeling diode, being connected in parallel with the inductive load, comes into play at this moment. As the voltage across the load reverses, the diode becomes forward biased. This allows the current induced by the collapsing magnetic field to flow through the diode, effectively bypassing the rest of the circuit. The diode provides a low-resistance path for this current, ensuring that the voltage spike is suppressed and the circuit remains protected. Freewheeling diodes find extensive use in a wide range of electronic circuits and systems. These small but mighty components play a crucial role in ensuring the longevity and reliability of various electronic devices. They are essential components in any application involving inductive loads, especially where switching operations are frequent. Inductive loads, such as coils and transformers, can generate high voltage spikes when the current flow is suddenly interrupted. One common application is in DC motors. These motors are widely used in various applications, from household appliances to industrial machinery. When the motor is switched off, the collapsing magnetic field generates a voltage spike that can damage the motor driver circuit. This spike can be quite substantial, potentially leading to costly repairs or replacements. A freewheeling diode placed across the motor terminals provides a path for this spike, protecting the driver circuit. By allowing the current to circulate through the diode, the spike is safely dissipated, ensuring the motor and its driver remain unharmed. Another common application is in relay circuits. Relays are used in many electronic systems to control high-power devices with low-power signals. Relays are electromechanical switches that use an electromagnet to open or close electrical contacts. This switching action can also generate voltage spikes, similar to those seen in DC motors. When the coil of a relay is de-energized, the collapsing magnetic field can generate a voltage spike that can damage the driving transistor or other components in the circuit. This can lead to malfunctioning of the entire system. A freewheeling diode placed across the relay coil provides a safe discharge path for this spike. By doing so, it protects the sensitive components in the circuit, ensuring the relay operates smoothly and reliably over time. Section 5. Safeguarding your circuits. The protective role of freewheeling diodes. The primary function of freewheeling diodes is to protect electronic circuits from potentially damaging voltage spikes. These spikes, if left unchecked, can lead to component failure, reduced circuit lifespan, and even complete circuit breakdown. By providing a low-resistance path for the flyback current, freewheeling diodes clamp the voltage spike to a safe level, preventing it from reaching other sensitive components in the circuit. This protective mechanism ensures the reliable and safe operation of electronic devices and systems, especially in applications involving inductive loads. Imagine a surge protector for your electronic devices. Just like a surge protector safeguards your valuable electronics from sudden voltage surges in the power line, freewheeling diodes protect electronic circuits from voltage spikes generated internally by inductive loads. Section 6. Advantages and disadvantages of using freewheeling diodes. Freewheeling diodes offer numerous advantages in circuit design and operation. These components are essential in many electronic circuits, providing a pathway for current to bypass certain parts of the circuit when necessary. They are simple, inexpensive, and highly effective in suppressing voltage transients. This suppression is crucial in protecting sensitive components from potential damage caused by sudden spikes in voltage. Their small size and ease of installation make them a convenient solution for a wide range of applications. Whether in consumer electronics, industrial machinery, or automotive systems, freewheeling diodes are versatile and reliable. Moreover, they improve the overall efficiency of the circuit by reducing energy losses associated with voltage spikes. This efficiency gain can lead to longer-lasting components and more stable operation of the entire system. However, there are also a few drawbacks to consider. While freewheeling diodes are generally beneficial, they are not without their limitations. One limitation is the small voltage drop across the diode when it is conducting. This voltage drop, although minor, can still impact the overall efficiency of the circuit. This can be a concern in low-voltage applications where efficiency is critical. In such scenarios, even a small loss can be significant, affecting the performance and energy consumption of the device. Another potential issue is the reverse recovery time of the diode. This is the time it takes for the diode to stop conducting after the voltage across it reverses. This recovery time can be significant for some types of diodes and can affect the performance of high-frequency switching circuits. In high-speed applications, this delay can lead to inefficiencies and potential circuit malfunctions. Therefore, while freewheeling diodes are incredibly useful, it is important to consider these factors when designing circuits to ensure optimal performance and reliability. Section 7. Alternatives to freewheeling diodes. While freewheeling diodes are a common and effective solution for suppressing voltage transients, alternative methods and components can also be used. These alternatives can offer different advantages depending on the specific requirements of your circuit, such as the desired level of voltage suppression, the speed of operation, and the overall cost. Understanding these alternatives can help you make a more informed decision when designing or troubleshooting your circuits. One alternative is to use a resistor capacitor or RC snubber circuit in parallel with the inductive load. The RC snubber circuit is designed to absorb the energy from the inductive load and dissipate it as heat, thereby reducing the voltage spike that occurs when the load is switched off. This method is particularly useful in applications where the voltage spike needs to be minimized to protect sensitive components. The RC snubber network can dissipate the energy stored in the inductor's magnetic field when it is switched off, reducing the voltage spike. This is achieved by the resistor and capacitor working together to smooth out the voltage changes, making the circuit more stable and reliable. Engineers often use RC snubbers in power electronics and motor control applications to enhance performance and longevity. Another option is to use a metal oxide varistor, or MOV, in parallel with the inductive load. MOVs are particularly effective in clamping high-voltage transients and are widely used in surge protection devices. They are made from a ceramic material that changes its resistance with the applied voltage, providing a dynamic response to voltage spikes. MOVs are voltage-dependent resistors that exhibit a sharp decrease in resistance when the voltage across them exceeds a certain threshold. This allows them to clamp voltage spikes effectively, protecting the circuit from potentially damaging surges. MOVs are commonly used in power supplies, telecommunications, and other applications where voltage spikes are a concern. This allows them to clamp voltage spikes effectively. By doing so, they help to maintain the integrity of the circuit and prevent damage to sensitive components. MOVs are a versatile and cost-effective solution for many applications. In some cases, the switching speed of the circuit can be reduced to minimize the voltage transient. This approach is often used in applications where high-speed switching is not critical, and the primary goal is to reduce the stress on the circuit components. This can be achieved by using a slower switching device or by adding a delay circuit. By carefully controlling the switching speed, engineers can significantly reduce the voltage transients and improve the overall reliability of the circuit. This method is particularly useful in applications where precise control of the switching characteristics is required. The choice of the most suitable method depends on the specific application requirements, such as the voltage and current levels, switching frequency, and cost constraints. Each method has its own advantages and trade-offs, and understanding these can help you select the best solution for your particular needs. Whether you choose freewheeling diodes, RC snubbers, MOVs, or another method, the key is to match the solution to the demands of your circuit. Section 8. Conclusion. Freewheeling diodes. Small component, big impact. Freewheeling diodes, despite their simple design and small size, play a crucial role in ensuring the reliable operation of electronic circuits. They are essential components in protecting circuits from potentially damaging voltage transients generated by inductive loads. By understanding the principles of diode operation and the importance of freewheeling diodes, electronics enthusiasts and hobbyists can design and build more robust and reliable circuits. Whether you're building a DC motor controller, a relay driver circuit, or any other electronic project involving inductive loads, remember the importance of incorporating freewheeling diodes to safeguard your circuits and ensure their longevity.